Hi class, this video is on topic D2, circuit analysis using Kirchhoff's laws, Ohm's law for parallel series and complex circuits. So the main goal by the end of this is to do circuit analysis for any circuit, even one that's a complex one looking like this, using Ohm's law and Kirchhoff's laws. So in this lesson, this is the organization of the lesson. We're going to do just a recap of circuit components and symbols, series, parallel, and complex circuits, some terms that you've learned from grade 9 electricity that are important moving forward. Then we're going to get into potential difference and Kirchhoff's law for that, current and Kirchhoff's law for that, some examples, and then equivalent resistance, some examples of resistance, and a few examples of circuit analysis. So this is quite a large lesson. It is okay if you view this video in two sittings and you just try the first half of the practice questions one day with the first half of the video, and then the next day the second half with the second half of the video with the second half of the questions. So it's important to know which standard circuit symbols we're using so that you can quickly draw a neat circuit. It really will help you solve circuit analysis problems. So the three parts of a closed circuit are power source, wire, and load. And the battery is the source of electrical energy, or sorry, the power source is the source of electrical energy. And it could be a battery or a power pack. So a power supply that you plug into the wall and you can dial up or down the voltage. The load is something that turns electrical energy into another form. So note that the load could be, we have wire. So the power source, the wire, and then the load. And the load could be one of a light bulb. So the light bulb turns electrical energy into light energy, a motor turning electrical energy into kinetic, or a resistor turning electrical energy into heat, or a number of other things. So sometimes we have simple diagrams. Sometimes we have complex diagrams, and it helps no matter what the load is, just to simplify it as a resistor. So you'll see some where we have just 7 resistors, and you might think, what's the purpose of this circuit? But we're just analyzing the connections with resistors in place because it's simpler to draw. So we're going to be using this battery, this wire, and this resistor for most of our diagrams. So do you remember what a series connection is from grade 9? So it's when there's only one path for the electrons to flow. When all of the connections in a circuit are series, then we call that a series circuit. And then a parallel connection is when there's multiple ways, multiple paths for the electrons to flow. And so if the whole circuit is only made up of parallel connections, if everything is connected in parallel, then the whole thing is called a parallel circuit. More often than strictly a series or strictly a parallel circuit, you'll see complex circuits, and this is the focus of grade 11. So make sure you're putting in a lot of time in your practice problems will be complex circuits. They're also called mixed circuits. So A and B are in parallel with each other, but they are in series with C and D. So it's like a parallel circuit within a series circuit. We call this mixed. And then you can get into, even more complex circuits, which we will solve for. So the 3 properties of electricity, as you remember from our last video, from the D1 task: potential difference, also known as voltage; current, symbol is I; electrical resistance, symbol is R; potential difference is V. And we need to fully understand these. So just a quick recap that the voltage is difference in electrical potential energy. So it's the difference in stored energy per unit charge. And you can kind of think of it like energy. Let's take a look at the path of electrons in a closed circuit to get a better understanding of voltage. So as electrons go across the battery, there is a voltage gain. As electrons go across the load, there is a voltage drop. And I think it's helpful to think of the analogy of the gravitational potential energy analogy. So if you imagine lifting up a ball over here, it has stored energy, and as soon as there's a clear path to the ground, the object naturally loses that potential or stored energy. And the EG gained here turns into EK over here once we let go. And if you think of that, the electrons gain potential energy across the battery that could be turned into something like electrical or kinetic energy on this side. So I find it's helpful to think of the voltage gain and voltage drop freezes as we talk about circuits. So whenever the voltage gained is across the battery, it has to be lost across all the loads. So if there's only one light bulb and you gain 6 volts across the battery, you will lose that 6 volts across the light bulb. And that will be reflected in the energy that you see, how bright the light bulb is. If you have a 6-volt battery that is connected to 2 light bulbs, you gain 6 volts across the battery, but that has to be distributed across 2 loads. So maybe you lose, I don't know, 2 volts here and 4 volts here. It does not have to be a 50-50 split, but it can be. It can be 3 volts and 3 volts. It depends on the resistance of each of the loads. Okay, so Kirchhoff's voltage law states that the voltage gains are equal to the sum of the voltage drops in a complete electron path in a closed circuit. So V1 plus V2 plus V3 equals V source. So maybe we have 3 volts plus 2 volts plus 1 volt equals 6 volts. And it's important to note that they might be identical resistances, which would make them the same voltage. So it could be 2, 2, and 2, but it doesn't have to be. So this is a very simple circuit. This equation only applies if it's a simple circuit. All connections are series. For all connections being parallel, we have this other equation. Notice it's not plus, it's equals. So there are 3 possible electron paths, 1, 2, and 3. Since an electron has 1 of 3 branches to choose from, no matter which path, the electron will only encounter 1 load in this case. So if you gain 6 volts up the battery, you're going to drop off 6 volts at that first branch if that's what the electron chooses, or 6 volts at the next branch, or 6 volts at the next. So the voltage across the parallel branches will always be the same. They won't always necessarily be the same as the source. That would only be if it was a strict parallel circuit, but if we put a resistor here, then this voltage value won't be equal to those. So the voltage across each parallel branch is equal. And you might recognize these mathematical statements from grade 9. These are located on your exam formula sheet. They are given to you. However, when we're given a complex circuit, there's no like one equation fits all. So you have to customize the equation. The more loads that are present, the more likely it is a complex circuit. And you have to customize your equation based on the circuit, the particular circuit. Even though we see both series and parallel connections, it's important that we can't strictly rely on grade 9 equations. It would be a mistake if we saw, oh, there's some connections in parallel, and we thought V1 equals V2 equals V3 equals V4 equals V5. So that is not true. Think of it, oh, well, do they all equal 72? They all equal each other and all equal 72? That cannot be true because we see that one is 36. So another mistake might be seeing, oh, okay, well, there's some connections in series. So thinking V1 plus V2 plus V3 plus V4 plus V5 equals 72 volts. That's not true either. Electrons have paths. So one true statement would be V source equals V1 plus V2 plus V4. And then it comes back around. Let me just pull up so another possible path is V source equals V1 plus V3 plus V5 if the electrons took that path. And we have 4 combinations here of those statements. So we actually have too many unknowns in those statements I've just stated, even though they are true. We might use those late in the problem. But what I would do in solving this problem is I would start by looking at, well, voltage across parallel branches are equal. So we know V2 is 20 volts. And then the voltage across here is equal. This voltage drop here is equal to that voltage drop. Now, we don't know either. So that's where we would have to go to V source equals V1 plus V2, which is 20. So 36 plus 20 plus something else equals 72. And that would give us the 16 volts here. So at first glance, these problems can be really intimidating, but try and think of like what are the simple statements that you know, and then you're building from there. Okay, going on to electric current, the review of electric current is that it's the rate of charge of flow. And we are going to be using conventional current. This is more important for my right-hand rules lesson. But it is true that for this whole unit, we're using conventional current flow. Even though we know electrons flow out of the negative into the positive, we're going to think of the current flowing from positive to negative and always include this arrow there. Kirchhoff also has a law to show the relationship between the currents throughout a circuit. So it states that the current entering a junction is equal to the current exiting a junction. So in the case of this simple series circuit, we don't have any junctions. So if there are no junctions, then the current stays the same. But there is a junction just means a split. So there's a fork in the road right here for the electrons. The 3 amps of electrons, which is coulombs per second, they reach this split, and some will go here and some will go here, and it depends on the relative resistances. How impeded are those electrons? If the more impeded they are, the more likely they're gonna take the other route. So maybe at that junction, we've got 1 amp in one direction, 2 amps in the other direction, and those add up to 3 amps. So we've got these 2 mathematical statements, which you should remember from grade 9. But of course, we need to know how to adapt these equations and customize them for complex circuits. These statements are still true for portions of the circuit. So it's still true that I source equals I1, but that's not equal to I2. It's still true that at this junction here, the electron flow going in, this plus this, equals the electron flow coming out. Yeah. So let's say if we have 6 amps coming out of here, that was from 4 amps and 2 amps. So 4 plus 2 equals 6. Same thing over here. Well, the 6 amps over here was the same all the way throughout. And we had 5 amps here. So if this was 6 and this was 5, well, this has to be 1. Okay, so if we try a quick practice problem, we can see that the current throughout here is the same. So I source equals I1, and then I2 equals I3. And then at this junction, we've got the total current of 4 amps that goes into the junction equals the sum of what goes here and here, which is 2 amps each. Then if we apply KVL, we have the source, which is like the total, equals V1 plus V2 plus V3. So we followed along this electron path and we got this statement, and that allows us to solve for V1. So 6 equals something plus 1 plus 2. That something is 3. And then the other electron path, there we go, is V source equals V1 plus V4. So some electrons will never see V2, will never drop off energy at lamp 2 and 3. So to solve for V4, we can write this statement, and we have got 6 minus 3 gives us 3 volts. And you might also say, oh, well, there's a shortcut, V2 plus V3 equals V4. That will work too. That is a consequence of these last two. If you put these two together, you can see V2 plus V3 equals V4. So you can use that as a shortcut if you do see it, if you're confident in it. So this is kind of like a Russian doll of mixed circuits, because we've got a series, which is like the baby, the series within the parallel circuit. So that's like a medium one within a series. So it's a series within a parallel within a series circuit, but overall we just call it a mixed circuit. And it helps to have tables like this to organize your answers. So recall, resistance describes how difficult it is for electric current to travel through a material. We have Ohm's law, which provides a relationship between potential difference, current, and resistance. We have, which is new, so the resistance definition shouldn't be new, but we have a new definition, and you should write this down in your student notes package. Equivalent resistance is the total resistance of a group of resistors in a circuit. So finding the equivalence resistance is like asking if we could replace all the resistors with only one resistor, and what would the ohms value be? So if we could collapse all three of these down to just one, what would be the ohms value? It would be just the same as adding them together. So if it was a simple series circuit, it's just addition. If it's just parallel, it's this fraction equation. 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over R parallel. So it's important to know how to take the reciprocal of your answer. So if we just have series 6 plus 6 plus 6 ohms, we can collapse those three together to get 18 ohms. So it's pretty easy. Note that these just happen to coincidentally have the same ohms value. We can certainly have several resistors in a row that do not have the same resistance value. So 6 plus 6 plus 6 plus 7 is 25 ohms. Okay, if we look at equivalent resistance to that circuit that we just analyzed, none of these relationships will fully get us to the answer of what is the ohms value if we replace all the lamps with one resistor. So step one is to collapse down the simplest portion of the circuit. So I said it's a series within a parallel within a bigger series. So we take the small series and we collapse it down to R2, 3, and that's just addition, R2 plus R3. And then we take R2, 3, and R4 and we collapse that down. So we collapse down the parallel branch and we get that equation, 1 over this, the sum of R2 plus R3 plus 1 over R4 is 1 over R parallel. Make sure you know how to take the reciprocal, because this is a common thing that we forget to do. And then to our final statement, we're going to collapse together that last equivalent resistance and lamp 1 to produce just one resistor. We could call that R total. So the reason why we'd want to do that is so that we just have, we're doing this collapsing in stages because we want to make use of true mathematical statements between resistances, and we want to simplify it down, and it really does help to solve problems this way. So let's try page 530, practice 1A. I've added this one from the textbook. I know there's a lot of examples in this video because I felt like you really need it, because this is a really big topic that could show up on final assessments. So let's try circuits connection looks like this, and all resistors are 5 ohms. First, we're going to collapse the smallest piece. So the smallest piece is R2, 3. This parallel equivalent resistance is 2.5 ohms. I remembered to take the inverse or the reciprocal. And then, why would I do that? Now that I have R2, 3, now it's just a series circuit of resistors. So now we can just add them all up and get 17.5 ohms. And we'll want to round to 2 significant figures because the numbers given in the question are with 2 sig figs. Okay, so now putting it all together. So believe it or not, all of those things are going to be done together in one question. So don't be intimidated. There is a strategy, and practice does make perfect. So the current, potential difference, and resistance is going to be analyzed at all points on a circuit so that all the missing values could be filled in. We're going to use a table to organize our answers. These are our tools. To recap, we have Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, and equivalent resistance formulas. Those formulas you can only strictly copy them out and use them if it's a simple circuit or a simple parallel. So if it's a complex circuit, you have to customize your equations based on the drawing. So what's helpful is rather than to look up your equations, well, Ohm's law always stays the same, but the other ones will change depending on your circuit connections. So what you should do is think of the key words in these laws. So for voltage law, follow the electron path, and its voltages add up to the source, the voltage source along the electron paths. And then Kirchhoff's current law, you're observing at the junction. So the amps in equals amps out. And then Ohm's law is just the same, no matter how complicated the circuit is. So that's why students, when you have a choice, students always choose Ohm's law. And there's going to be some choice of what steps you start with or what steps you use. And so I highly recommend choose Ohm's law whenever possible. And then equivalent resistance, you're going to analyze the circuit structure. So I said, well, we had a series inside a parallel, inside a series. So you're going to look at sort of the hierarchy of circuit structure. There's a really great video, in addition to this video, that I'm going to recommend that you watch. It does not go over as many examples, but it is a recommended video resource. Okay, so let's pull up example 1. Complete the circuit analysis for this simple series circuit. So it is a series circuit. Let's complete the circuit analysis for this simple series circuit. So it is a series circuit because there are only series connections between the two resistors. I've drawn a very neat diagram and with a ruler, and I've labeled the positive and negative terminals of the battery. I've labeled conventional current, which is what we're using in this course. Although I have to admit the most important time that you remember that is once we get to the right-hand rules in the next video. So for circuit analysis, I strongly recommend that you draw a neat table organizing the V, I, and R for each of the components of the circuit. And this will do a couple of things. It will help keep your work, it will establish what your final answers are. It will help organize your givens. And if you ever get stuck, there's a strategy for moving forward. So moving forward, the goal of circuit analysis is to fill in all of these blank spots. And working horizontally, the relationship between V, I, and R at any point in the circuit is Ohm's law. Vertically, the relationship is KVL, KCL, or a custom equivalent resistance formula. So what I do is you're going to determine the number of rows is based on the number of resistors plus 1, because you have 1 row for each resistor, or each light bulb, each resistor, each motor, whatever the load is. So I guess 1 for each load plus 1 for the source. So we have a 3-row table for this particular circuit. And if the circuit got more complicated, we'd just keep adding rows. So I filled in the givens, and I usually do that in pen. I draw the table with a ruler in pen. I draw everything that's given in pen so that I'm filling in my intermediate answers in pencil. And worst case scenario, if I have to just start the whole thing over again, I can take an eraser to the whole thing. And then the givens I don't have to fill in. So in this case, I would observe horizontally. I can't move forward with Ohm's law for any row because I don't have 2 out of the 3 for any row. But vertically, I have all the resistances except for our equivalent resistance of the whole circuit. So my first step will be equivalent resistance. So for each step, you're gonna write a number and caption it, and then you're gonna write the math. And this is the most organized way to do it. This is gonna really help you check your own work and help others understand your work. So for equivalent resistance, we have R in series is equal to, in this case, R1 and R2 are connected in series, so it's R1 plus R2, 5 ohms plus 7 ohms gives us 12 ohms. So now I've done this either like in a color or pencil, and then that same color or pencil, I'm gonna fill it in for a final answer of 2 sig figs. So I'm locking in my sig figs in this table. Actually, while we're talking about communication marks, the header of every table should indicate the units so that you don't have to repeat those units throughout the whole, for every entry in the table. Okay, now that we have equivalent resistance, now that we solved for equivalent resistance of the entire circuit, that's if all of the resistors were replaced by 1, now I have 2 out of the 3 of the first row. So now for my second move, I'm going to use Ohm's law to solve for the current through the source. So we have V equals IR, and since we're talking about the source, it's the voltage gain across the source equals the current through the source times, it's really the equivalent resistance, but if you call it R source, I will know what you mean. So I source is equal to V over R, which is 6 volts divided by 12 ohms, which is 0.5 amps. And if we report it with the proper number of significant figures, it will be 0.50. Okay, now scanning over the rows, there are no rows that we can move forward with Ohm's law. And we've already used our equivalent resistance tool, so KVL or KCL, can you see any opportunities to use KVL or KCL? Well, in KCL, when we're talking about there being no split, no junction, the current is just the same the whole way through. So for my third step, I'm gonna solve for I2 and I1 using KCL. So the current to the source is equal to the current through 1, which is equal to the current through 2 because they are in series. And I don't even have to write numbers to that. You do have to record something to show your process work for that. So you can just fill down the column for current. And finally, our last step, the only thing that is left for us to do is to solve for these last 2 spots. Here, as with any last steps of a circuit analysis, you actually have choices. If you really like Ohm's law, you can solve for it using V equals IR. So just current times resistance gives you that value. So that's one choice. I'm going to choose to use KVL, which is working vertically through that column because we haven't done that yet. And just to show you one, oops, this is supposed to be not KCV, KCL. That's Kirchhoff's current law. So I'm going to say we're going to use KVL to get V1 and V2. So I know that in one electron path, so KVL is where we look at the electron path. The electron path is over here. So we go that way, then this way, then this way. Technically, the electron path is from the negative to the positive, but it doesn't really matter. The path is continuous, whether you use conventional current or the actual electron path. The math is the same. We've got V source equals V1 plus V2. Oh dear, we have V source, we don't have V1 or V2. So we actually are going to need Ohm's law to find V1, and then we're going to sub that in here. It's going to be a known. So V1 equals I1 R1. So current 1 is 0.5 amps. Resistance 1 is 5 ohms. So we get 2.5 volts. So now we have 2 out of the 3, and we can solve for V2. So now this is actually just solving for my V2. So in this last step, we're using Ohm's law and KVL to find the last two. V2 equals V source minus V1. So if this is what we're solving for, you rearrange to solve for that. I'm not sure, hopefully the contrast is good enough that you can see. This is a brand new marker, so it is very pointy. So 6 volts minus 2.5 volts is 3.5 volts. 3, 4, 5, 6. So 3.5 goes here and 2.5 goes here. Now, if you were to scan this solution, not only can you see the givens are in pen and the intermediate answers are all in pencil, you can scan over to see do you have the significant figures of your final answers in this table? And you can trace your work a lot better than if you just, in grade 9, you'd probably just dumped all the numbers into that and you didn't show your work. This might seem like a trivial example, but trust me, it gets more challenging from here. So baby steps. Example 1. So at the end of every circuit analysis problem, you want to check within your table that every row satisfies Ohm's law, and you want to look based on circuit connections that KVL and KCL are satisfied, because you don't necessarily have to use Ohm's law for each row. So there is, the good news is about these problems is there always is a way to check, and you should practice double checking. Now for example 1B, just because this video has a lot of examples, I've decided to post it as a separate video in case you need more examples. So that was an example of strictly series, and now this is an example of strictly parallel. The video that I posted is with different resistance values than your student notes package, so just note that when you are watching the video and completing it. So we're going to go on to a complex mixed circuit. Or mixed circuit. So this circuit is mixed because we have a parallel connection within a series connection, and that makes it a mixed circuit. I've labeled my positive negative terminals, conventional current. I've drawn a VIR table which organizes the VIR for each component in the circuit. And so taking a look at what options we have to start. Horizontally, like if you look at the rows, we don't have 2 out of the 3 pieces of information for any row, so we can't start with Ohm's law. Can we start with KVL? KVL looks at an electron path. Notice there are 2 different electron paths, but we know that V1 plus V2 must add up to 12. We don't know either V1 or V2. We know V1 plus V3 must add up to 12, but we don't know V1 or V3. So this is not going to be a good first, it's not going to be a possible first step. KCL, we know that the current splits here. So unless we know the current going in and one of the branches going out, or both branches going out, and we can solve for the one going in, basically we have no other choice but to start with the resistance column. And you'll notice once you do several practice problems, whenever all the resistances are given, the first step is going to be finding the equivalent resistance. So equivalent resistance. We're going to label our steps. Now, the temptation here is just to do R1 plus R2 plus R3. I think that's because maybe you recognize this from grade 9. But in grade 9, that would be only for a strictly series circuit. This is parallel here, and then series here. So our first step is going to be drawing, or well, you don't have to draw it, but collapsing down R1 and R2 into R23. And then the reason why we do that is because then we just have a series connection between R1 and that equivalent resistance for the parallel bridge. So 1 over R23, we're going to use the parallel formula because it's a parallel connection. 1 over R2 plus 1 over R3. To get R23, we're going to have to end up doing the reciprocal of this. So 1 over 25 ohms plus 1 over 35 ohms. I usually write to the power of -1. And there is a button on your calculators that looks like that. That is the button on your calculator that you're going to want to find in order to flip your answer. So you're going to do 1 divided by 25 plus 1 divided by 35, and then flip your answer by pressing that button. And you should get 14.5833. So I said one common mistake is just to add up the resistance column and slap that down for sort of the total resistance. That's not true because it's a complex circuit or a mixed circuit. So now that we realize we have to collapse using the parallel resistance formula, and then we can add these two together. The temptation is just to put this number in there. This value is just for R23. So now the final step to add them all together, it would be R, sometimes I call it R total to mean the equivalent resistance. If we were to, let me get a different color so it's a little bit more visible. If we were to collapse these two together and replace it with just one resistor. R total is R1 plus R23. So R1 was 15 ohms plus, we're going to use the answer button, not some rounded number. There's no interest, there's no point in rounding this number ever because it doesn't go in the table as a final answer. It's just an intermediate answer, and we don't want to round intermediate answers. Equals 29.5833 ohms. Now that's the number. That's our equivalent resistance. If we were to take all three of these resistors and replace it with one resistor, the equivalent resistance would be, two significant figures. I guess we're going to have to round it, or is it 3? Oh, it's 3 significant figures. Because otherwise, if that was 30 with 2 sig figs, we'd have to use scientific notation, and I haven't left a whole lot of room here. So 3 sig figs is fine by me, 29.6. Oh dear, we need to have units in our headers. You might say, well, resistance is always ohms and current is always amps, but no, you could have milliamps or mega amps, or you could have a prefix with the amp. So it's important to put the unit there. So we have our total, and we're going to round it for the purpose of the table, but we're going to keep the entire value because maybe we need to carry it forward. And in fact, we do need to carry that forward because if you look, we're still, KVL and KCL still would be a dead end. We couldn't move forward with it. We can now move with Ohm's law at the source. So our second step is Ohm's law to solve I source. And we know V equals IR, which means I equals V over R. Voltage is 12 volts. Resistance is 29.5833. You can just put 29.6 here, but you better use your answer button on your calculator. So when I use the answer button on my calculator, I get 0.40563 amps. So that number I'm going to round to 3 sig figs for the purpose of the table. But I'm going to keep the full the full answer just in case I need to carry it forward. And then what other moves, what other options do we have here? It doesn't look like we can move forward with Ohm's law for any row, but now we have to start somehow using KVL or KCL. So let's start with, so KVL, we can't move forward with it because of the same reasons at the beginning we couldn't start with it. KCL is, does this current lead to some other location without being split? And it does, right here. The current through the source is the same as the current through resistance 1, and you don't reach the split yet. So 0.406 is our answer for that spot as well. I am going to write that out to justify that answer. KCL tells me that I source is equal to I1. Okay, now can we continue further with KCL? I want to know how it splits. Is it going to split exactly in half? So if there's a 0.4, is it going to be 0.2 and 0.2? So take a moment to pause, see if you can think of, is that going to be true? Is it going to split evenly? It's not going to split evenly because there's a lot more resistance on branch 3. That means that more current will go here. Maybe this is 0.3 and 0.1, or 0.35 and 0.05. So we don't know how it splits. We just know that they add up to 0.406. So that might be useful later, but we can't mathematically, we can determine possibilities of how it splits, but we can't determine exactly how it splits. So I don't know, can we look at KVL? Vertically, is there anything that we can say? We know that, oh yeah, we can't move forward with KVL for the same reason we couldn't start with it. This is not enough information, just knowing this one. So, oh look, horizontally we can use Ohm's law for V1. That's good. So step 4 is we're going to use Ohm's law to find V1. So V1 equals I1 R1. And for V1, we have 0.40563 amps. So we're going to, we're not going to round it. We're going to use the unrounded version. Sorry, is there too much shadow there? Resistance is 15 ohms. So answer button times 15, we should get 6.0845 volts. We sub that in here, 6.08. So that's a full answer, V1. Okay, we're still not done. We still have these 4 boxes, and yet we've done a lot of work. So you can see when you add more resistors, there's a lot of value in organizing your answer in a table, in color coding, if that's an option for you, or if you like doing that. Can we move forward with KVL? Since I'm writing in purple, I'd like to maybe continue in this small space over here. So KVL is looking at an electron path. There is one electron that will go from, well, not one electron, but one electron path is V1, V3, and that has to add up to V source. So we can use, for step 5, we can use KVL to find V2, and actually V3. So if we know V source is equal to V1 plus V3, we know V source is 12, and we know V1 is 6, or 6 and a bit, so then we can find V3. V3 is equal to Vs minus V1, which is 12 minus 6.0845 volts. So what do we get for that subtraction? 5.9. 5.915. I hope I'm not writing too small there that you can still see it. So I'm going to put that in, 5.92. And also V source is V1 plus V2. So V2 is also equal to 5.915. Now, maybe you didn't write this line. Maybe you wrote a line that said, what is it? V2 equals V3. And that would be, oh, hopefully you can see this. That would be true if you just want to say V2 equals V3 because I know the voltage across parallel branches is the same. So you could do it that way. But either way, you get the same numbers here. And these two voltages because they're parallel branches. And then our very last step, we can use Ohm's law. We can use Ohm's law as our very last step. So I'm going to do that on the next page. So 6, good old Ohm's law to find V2 and V3. We know V equals IR. So that means V2 equals I2 R2. So I2, oh, sorry, we're solving for I2 and I3. That's good, you can't even see where I wrote the wrong thing. I2 plus I3. So I2 is equal to V2 over R2. And we have 5.915. So we're going to use the unrounded number. Divided by R2, it was exactly 25 ohms. And we're going to do the same thing just right away. You don't have to show your work if you've just done the exact same algebraic rearrangement. V3 is the exact same number. And this time it's divided by 35 ohms. So just calculating those. We've got our calculated answers here, 0.2366, 0.169, and we're gonna round those to 3 significant figures and put those in our final table, and it's very satisfying to get to fill in the very last numbers, knowing that we're done. Okay, double checking, every row must satisfy Ohm's law. Every column you must consider KVL, KCL, or equivalent resistance. Yeah. So that is a complex or mixed circuit example where you are given all the resistances except for that top row there. Okay, so example 2, it was a complex circuit, but we were given all the resistance values. The next example, notice that you're not given all the resistance values and the solution looks a little different and you have to use problem solving. You have to be maybe a little bit creative. There's more than one way to solve this problem. So I'm going to post a different video for this problem because it is a longer problem solving question, and I think that you should start the practice questions, and then when you come across one that is more complex, if you feel that you need this video, then you can go to that one. So for the practice videos, or for the practice questions, I've actually outlined the description of that practice problem and the reason why I selected it so that you can see that you're getting one of every different type of problem and you want to practice at least one of each of these different problems. So make sure to complete the exit ticket and submit these practice problems once you complete them. It's really important to do this practice because the learning goal based on this video is skills based. It's, do you have the problem solving skills and are you able to apply Ohm's law and Kirchhoff's law? It's not memorization and regurgitation. So you really have to practice so that you can make perfect. Have a great day, stay safe. And make sure to check out the recommended videos at the end of this video and in the comment section. Have a great day.